All right, welcome back everyone to the deep dive.
Good to be back.
So you've just spent some time getting familiar with the basics, right? Atomic structure, particles.
Isotopes, yeah, nuclear symbols, the real fundamentals of what atoms are.
Exactly. You've kind of got a grip on the what of chemistry.
Right, the building blocks.
The chemistry, well, it's really about what happens when these things interact, chemical changes.
Mhm.
And a huge part of that is figuring out the quantities. How much stuff do I need? How much product will I get?
What if I don't mix them perfectly? All those how much questions.
Yeah. And that's where stoichiometry comes in, right?
That's the term, yeah. Stoichiometry. It's the quantitative side, moving from just identifying things to actually measuring and predicting amounts in reactions.
Okay, so that's our mission today. We've gathered your notes, some textbook excerpts on atomic mass, the mole, molar mass, chemical equations, all that quantitative stuff.
And we're going to unpack it, pull out the key ideas to help you really get a solid handle on this.
Let's dive in. Where do we start? Atomic mass.
Makes sense. We need a way to talk about how heavy these atoms are. You can't just weigh one atom.
Right. Definitely not on any scale I've seen.
Exactly. So chemists needed a standard. The modern system, set up back in the 60s, it's based on one specific isotope, carbon-12.
Carbon-12, okay.
By definition, one atom of carbon-12 is assigned a mass of exactly 12 atomic mass units. We use a lowercase u for that unit.
So everything else is measured relative to that carbon-12 standard.
Precisely. It's a relative scale.
Okay, but then the number on the periodic table for carbon is like 12.0111, not exactly 12. What is that?
Good question. And it connects directly back to what you just learned about isotopes.
Okay.
That number 12.011 is the average atomic weight. It's a weighted average, you see. It takes into account all the naturally occurring isotopes of carbon, mostly carbon-12, but tiny bits of carbon-13 and carbon-14 too, and how abundant each one is.
Right. So the existence of isotopes explains why most atomic masses aren't nice whole numbers. That clicks.
Exactly. It links the atom structure directly to this quantitative measure.
Okay, so U is the unit for one atom. But we work with like massive amounts of atoms in the lab. Trillions and trillions.
Billions of trillions, even more, which is where the mole comes in.
The mole. Okay, what is a mole, really? It sounds a bit abstract.
Hey, yeah, it can seem that way at first, but honestly, think of the mole simply as a number, just a specific quantity.
Like how a dozen means 12.
Exactly like that. A mole is just the chemist's really, really big dozen. It's Avogadro's number.
Which is 6.022 times 10 to the 23rd.
That's the one. So 1 mole of anything, atoms, molecules, ions, whatever, contains that many units of it.
That number is just staggering. Hard to even picture.
It really is. But it's incredibly useful because of how it links things.
Links what?
It links the microscopic world of single atoms and molecules measured in U to the macroscopic world we work with in the lab measured in grams.
Okay. How does Avogadro's number make that link? Give me an example from the source.
Sure. The source says 1 mole of copper atoms is 6.02 by 1023 copper atoms.
Okay.
1 mole of carbon dioxide, CO2, molecules. That's 6.022 by 1023 CO2 molecules. 1 mole of sodium ions.
6.022 by 1023 sodium ions. It's just that specific count.
You got it. It's purely a count.
But the link to mass, how does this number help us weigh things out?
Here's the really elegant part. It's set up so that 1 mole of any element has a mass in grams that is numerically equal to its atomic mass in U.
Wait, really? The number on the periodic table?
The very same number.
So carbon's atomic mass is 12.011 U. You're saying 1 mole of carbon atoms weighs 12.011 grams.
Precisely. That's the magic. Iron, A, has an atomic mass of about 55.845 U. 1 mole of iron atoms weighs 55.845 grams.
Whoa. Okay, that is convenient. So I can just look at the periodic table value and know the mass of 1 mole in grams.
Spot on. That's exactly why the mole is so fundamental. Remember, though, 1 mole of different elements has the same number of atoms.
Avogadro's number.
Right, but they'll have different masses in grams because the individual atoms themselves have different masses.
Okay, that makes sense. And this mass of 1 mole, that's called the molar mass.
Exactly, molar mass. It's the mass in grams of 1 mole of a substance. The units are grams per mole.
So it's just the atomic mass number or the molecular mass or formula mass number, but with units of Gmol.
You've got it. The source gives examples. Carbon, atomic mass 12.011 U, molar mass 12.011 Gmol.
Right, and for compounds too, like ethanol, C2H5OH.
Yep. Ethanol's molecular mass is 46.069 U, so its molar mass is 46.069 Gmol. Calcium phosphate, C3PO42, formula mass 310.177 Gmol.
Okay, the number stays the same, just the unit changes, meaning from mass of one particle to mass of 1 mole of particles.
And how do we find that molar mass for a compound, say water, H2O? Do we just add up the parts?
Pretty much. You sum the atomic masses of all the atoms shown in the chemical formula. For H2O, you have 2 hydrogens and 1 oxygen.
So using the values from the source's calculation, 2 times the mass of H plus 1 times the mass of O.
Exactly. 2 1.01 gmol plus 1 16.00 gmol gives you 18.02 gmol for water's molar mass. And the source did similar sums for K4 136.141 gmol and urea CONH2 60.0553 gmol. Same process.
Same process. Add up all the atomic masses from the periodic table according to the formula. It's a calculation you'll do all the time.
Okay. So we have atomic mass, U, the mole, a number, and molar mass. How do we actually use these to convert between, say, grams I weigh out and the number of atoms or molecules or moles?
It's all about using them as conversion factors, just like converting feet to inches. The mole is your central hub.
The hub.
Yeah, you use molar mass, gmol, to convert between grams and moles, and you use Avogadro's number, particles mole, to convert between moles and the actual number of particles, atoms, molecules, etc.
Oh, like that flow diagram in the notes. Mass, moles, particles.
Exactly that diagram. Moles are the bridge. You almost always convert to moles first, or from moles last.
Let's try an example from the source. Say 5.00 by 2020 atoms of cobalt. Tiny Matt, how many grams is that?
Okay, you start with atoms, you want grams. Path is atoms, neomoles, milligrams.
Step 1, atoms to moles. Use Avogadro's number.
Right, set it up so atoms cancel. 5.00 by 1,020 atoms. 1 mole, 6.02 by 1,023 atoms. The source calculation gives 8.30 by 10 to 4 mole of cobalt.
Okay, now I have moles. Step 2, moles to grams. Use molar mass.
Yep, cobalt's molar mass is about 58.93 gmol, according to the source. So 8.30 by 10 to 4 mole, 58.93 g1 mole. Moles cancel.
Leaving grams, and the answer was 4.89 by 10 to 2 grams, less than 0.05 grams.
That's it. Shows you just how many atoms are in even a tiny speck of material.
Wild. Okay, what about going the other way? Grams to molecules, like that glutamic acid example, start with 245.3 grams.
Okay, grams to molecules, path grams, moles, more molality.
First, grams to moles. Need the molar mass of glutamic acid. The source uses 147.1293 g.
Right, so 245.3 g, 1 mole, 147.1293 grams. Grams cancel. Now you're in moles.
Next, moles to molecules. Use Avogadro's number again.
Correct. Multiply by 6.022 by 1,023 molecules, 1 mole. Moles cancel.
So the whole calculation chained together like in the sources, and you end up with the number of molecules.
Precisely. Mastering these conversions, grams to moles, moles to particles, and back again, is absolutely crucial.
Got it. Moles are the key. So now we can count and weigh stuff. How do chemists actually describe what happens when substances react?
That's where chemical equations come in. They're like the sentences of chemistry.
Like sentences.
Yeah, the chemical formulas are the words, and the equation tells the story of the reaction. You have your starting materials, the reactants, on the left, an arrow indicating the change, and the substances formed, the products, on the right.
Reactants yield products. And there's a really fundamental rule here, right, from the source. Atoms aren't created or destroyed.
The law of conservation of mass, absolutely critical. In a chemical reaction, atoms just get rearranged. You end up with the same number of each type of atom you started with.
Which means the equation has to be balanced.
Exactly. A balanced chemical equation reflects that conservation. It has the same number of atoms of each element on both the reactant side and the product side.
How do we balance them?
You add coefficients numbers in front of the chemical formulas. You tweak these coefficients until the atom counts match for every element. You never change the subscripts within a formula because that would change the substance itself.
Right, like the methane example. CH4 plus O2 ECO2 plus H2O. That's unbalanced as written.
Correct. Check the atoms. 1C left, 1C right, okay? 4H left, 2H right, nope. 2O left, 3O right, 2 and CO2, 1 and H2O, nope.
So the source shows balancing it by putting a 2 in front of O2 and a 2 in front of H2O.
Right, CH4 plus 2O2 plus 2H2O. Now, check again. C, 1 left, 1 right. H4 left, 2 to 4 right. O2 to 4 left, 2 plus 21, 4 right. Now it's balanced.
And those coefficients, the 2's and the unwritten ones, are super important.
They are. We'll get right back to them. The source also mentions the little letters in parentheses sometimes. S, L, G, A, Q.
Oh yeah, state symbols.
Just tells you the physical state. Solid, liquid, gas, or aqueous dissolved in water. Useful extra info.
And briefly, the source mentioned balancing charge too, for ions.
Yeah, if you have charged species involved, the total charge must also balance. Left side total charge must equal right side total charge.
Okay, balanced equations are key. Now, let's connect it all. How do we use these balanced equations to finally answer those how much questions? This is the stoichiometry calculation part.
This is it. This is where we use the quantitative relationships from the balanced equation to figure out amounts, how much reactant is used up or how much product is made.
And rule number one is you absolutely need a balanced equation first.
Cannot emphasize that enough. Without the balanced equation, any calculation you do will be wrong, because the balanced equation gives you the crucial link.
Which is?
The mole ratio.
Mole ratios. Tell me more.
The coefficients in the balanced equation, those numbers in front, tell you the ratio in moles of how substances react and form.
So back to methane. CH4 plus 2O2 plus 2H2O. The coefficients are 1, 2, 1, 2.
Right, so that tells us 1 mole of CH4 reacts with exactly 2 moles of O2. And when they react, they produce exactly 1 mole of CO2 and 2 moles of H2O. Those are the mole ratios.
And these ratios become conversion factors. Like I could write 2 mole O2, 1 mole CH4, or 1 mole CH4, 2 mole O2.
Precisely. Or 1 mole CO2, 1 mole CH4. Or 2 mole H2O, 2 mole O2, which simplifies to 1 mole H2O, 1 mole O2. These ratios let you convert between moles of one substance and moles of another in that specific reaction.
Okay, let's use the source example. If you start with 6.75 mole of CH4, how many moles of O2 are needed?
You know moles of CH4, you want moles of O2. Find the mole ratio, linking them from the balanced equation.
That's the 1 CH4 to 2 O2 ratio, so 2 mole O2, 1 mole CH4.
Perfect. Now multiply your starting moles by that ratio. 6.75 mole CH4, 2 mole O2, 1 mole CH4.
Mole CH4 cancels, leaves mole O2. And 6.75 times 2 is 13.5, so 13.5 mole O2 needed.
That's a direct mole-to-mole calculation, simple and powerful.
But often we measure mass, not moles, in the lab, so we need to link mass calculations with these mole ratios.
Exactly. We combine the molar mass conversions, grams milliliters equals moles, with the mole ratio conversions, moles A, moles B, that flowchart idea again.
Mass A, moles B, mass B. Is that the usual path?
That's the most common pathway for gram-to-gram calculations. You have to go through moles using the mole ratio from the balanced equation as the bridge between substance A and substance B.
Okay, let's tackle that propane C3H8 example from the source. Given 96.1 grams of C3H8, calculate grams of O2 needed. The balanced equation is C3H8 plus 5O2, 3CO2 plus 4H2O.
All right, start with a given, 96.1 G C3H8. First step.
Grams to moles.
Yeah.
Use the molar mass of C3H8. The source uses 44.1 G mole.
Right, so 96.1 G C3H8, 1 mole C3H8, 44.1 G C3H8. Grams cancel. Now we're in moles of C3H8.
Next step, bridge to the substance we want, O2. Use the mole ratio from the balanced equation.
Which is?
1 C3H8 to 5O2. So the ratio is 5 mole O2, 1 mole C3H8.
Excellent. Multiply by that. 5
Right.
mole O2, 1 mole C3H8. Moles C3H8 cancel. Now we're in moles of O2.
Final step, moles of O2 back to grams of O2. Use the molar mass of O2, which is 32.2 G mole.
Good. Multiply by 32.0. O2, 1 mole O2. Moles O2 cancel.
So the full setup, chaining all the conversions as shown in the source.
And doing the math gives the answer from the source. 349 green O2.
Wow, okay. Start with gram, end with grams, but you have to go through moles in the middle using that balanced equation ratio.
That's the heart of stoichiometry right there.
But like we said, real life isn't always that neat. What happens when you don't have the exact stoichiometric amounts? You just mix some stuff together.
Yeah, that's far more typical. And it leads us to the concept of the limiting reactant, or sometimes called the limiting reagent.
Limiting reactant, meaning...
It's the reactant that gets completely used up first in the reaction. It runs out.
And because it runs out, it limits things.
Exactly. It limits the maximum amount of product that can possibly be formed. Once it's gone, the reaction stops, even if you have plenty of the other reactants left over.
Why is knowing this important, besides just knowing the reaction stops?
Well, the source mentions a few key reasons. Industrially, if one reactant is really expensive, you'd want to make it the limiting reactant and use an excess of the cheaper ones to make sure all the expensive stuff reacts. Less waste.
Makes sense.
Or think about rocket fuel. You want the fuel and oxidizer to react almost perfectly in their stoichiometric ratio. You don't want tons of unreacted fuel or oxidizer left over just adding dead weight. So controlling the limiting reactant is crucial for efficiency.
Okay. The source had that sandwich analogy, which was pretty helpful. Recipe: 2 bread plus 3 meat plus 1 cheese minus 1 sandwich.
Right. And you have 8 bread, 9 meat, 5 cheese. How many sandwiches can you make?
You figure out how many sandwiches each ingredient could make if the others were unlimited.
Go ahead.
Okay. Bread: 8 bread, 2 bread sandwich, 4 sandwiches. Meat: 9 meat, 3 meat sandwiches, 3 sandwiches. Cheese: 5 cheese, 1 cheese sandwich, 5 sandwiches.
So which ingredient limits you?
The meat, because it only lets you make 3 sandwiches, which is the smallest number. You run out of meat first.
Exactly. Meat is the limiting ingredient, And the maximum number of sandwiches product you can make is 3.
Okay, that makes sense. How do we apply that logic to a chemical reaction? The source gave 2 ways to find the limiting reactant.
Method 1 is just like the sandwiches. Calculate the amount of product, usually in grams, that could be formed from the starting amount of each reactant, assuming the others are present in excess.
And the reactant that gives the smallest amount of product is the limiting one.
Correct. That smallest amount is also your maximum possible yield, which we'll call the theoretical yield in a moment.
What's the second method?
Method 2 is sometimes quicker if you only need to know which reactant is limiting. You convert all your starting reactant amounts to moles, then you divide the moles of each reactant by its stoichiometric coefficient from the balanced equation.
Okay, moles divided by coefficient.
The reactant that gives the smallest result from that division is the limiting reactant.
Let's try the ammonia NH3 and copper 2, oxide, CuO, example from the notes. Given 18.1 gram NH3 and 90.4 grams CuO, balanced equation. 2NH3 plus 3CuO, N2 plus 3Cu plus 3H2O. Let's use method 1. Calculate grams of N2 from each reactant.
Okay, starting with 18.1 gram NH3.
So the ammonia could make 14.9 grams of N2 if it all reacted. Now for the CuO.
So the CuO could make 10.6 grams of N2. Now compare.
14.9 grams N2 from ammonia versus 10.6 gram N2 from copper oxide. 10.6 is smaller.
Meaning
Meaning the CO runs out first. CuO is the limiting reactant.
correct. Now let's quickly check with method 2. Moles divided by coefficient. We need moles first. Moles NH3 is 17.1 gram is 17.03 billion at 1.06 mole. Mole CO series was 90.4 grams, 79.55 gram at 1.14 mole. Okay, now divide by coefficients. NH3 coefficient is 2, CuO is 3.
So for NH3, 1.062 equals 0.530. For CuO, 1.143 equals 0.380.
0.380 is smaller than 0.530, and 0.380 came from Cu.
Confirming that CuO is the limiting reactant. Both methods work. Second one is often faster just to ID the limiter.
Yeah, the source showed that HCl and K2CO3 example, using method 2 really quickly too, found K2CO3 was limiting.
It's a useful shortcut sometimes.
Okay, so the limiting reactant determines the maximum possible amount of product. What's the official term for that maximum amount?
That's the theoretical yield. It's the amount of product, usually in grams, calculated based on the limiting reactant, assuming the reaction goes perfectly to completion with no losses or side reactions.
But so in our ammonia example, the theoretical yield of N2 was 10.6 grams. That's the most you could possibly hope to make from those starting amounts.
Exactly. It's a calculated value, the ideal outcome.
But chemistry in the real world labs,
Yeah.
they're messy. You probably don't actually get 10.6 grams, right?
Yeah. Almost never. Things happen. Maybe the temperature wasn't quite right. Maybe some side reactions occurred. Maybe you lost some product during purification. Maybe the reaction didn't have enough time to finish. The source lists several reasons.
So the amount you actually collect in the flask at the end, that's different.
That's called the actual yield. It's what you physically measure after the experiment is done, and it's almost always less than the theoretical yield.
How do we describe how well the reaction worked then? How close we got to the maximum?
That's the percent yield. It's a measure of the reaction's efficiency.
How is it calculated?
Simple ratio, percent yield, actual yield, theoretical yield, 100%.
Okay, let's wrap up the ammonia example. Theoretical yield of N2 was 10.6 Gs. The source says, let's imagine you actually collected 7.5 grams of N2 in the lab.
So the percent yield would be 7.50, 10.6 G, 100%.
Which comes out to 70.8%, according to the source.
Right. So in this hypothetical experiment, the reaction was 70.8% efficient at producing nitrogen under those conditions.
That seems like a really important number for any experimental chemist. Tells you how good your process is.
Absolutely. It's a key indicator.
Okay. Wow. We've definitely unpacked a lot from those notes. Let's do a quick recap.
Sounds good. We started with stoichiometry itself, the whole idea of quantities in chemistry.
Then the basics. Atomic mass unit, U, based on carbon-12, and how the periodic table value is an average accounting for isotopes.
Then the big one, the mole. Avogadro's number, 6.022 by 1023, as just a count.
And the crucial link, molar mass, mole, letting us connect the mass we weigh to the number of moles.
We talked about using molar mass and Avogadro's number as conversion factors, always using moles as the central hub. Mass, moles, particles.
Then shifted to reactions. Chemical equations is the language, and the absolute necessity of balancing them to conserve atoms.
And how those coefficients in the balanced equation give us the vital molar ratios, the conversion factors between different substances in a reaction.
Which lets us do stoichiometry calculations, using mole ratios, often combined with molar masses, to calculate how much reactant is needed or product is formed, like mass A, mole B, mass B.
Then we hit the real-world complication, the limiting reactant, the one that runs out first.
We saw how to identify it, either by calculating product from each reactant or the Molesko-efficient trick.
And how the limiting reactant dictates the theoretical yield, the maximum possible product.
Finally, comparing the actual yield, what you really get, to the theoretical yield gives the percent yield, measuring efficiency.
That covers the core concepts. These are the tools you need for quantitative chemistry.
Absolutely. Getting comfortable with moles, balanced equations, mole ratios, limiting reactants.
Yeah.
It's fundamental for lab work, for understanding reactions.
It really underpins so much of what you'll do next. Practice those conversions and calculations. It makes a huge difference.
Definitely. And, thinking about that limiting reactant idea, here's something to mull over. Based on the themes we discussed from the source material, we talked about using the limiting reactant to maximize use of an expensive chemical. But how else could strategically choosing your limiting reactant influence how you design an experiment? Could it maybe help you control which reaction happens if multiple products are possible? Or minimize difficult-to-remove byproducts? It's not just about yield. Maybe it's also about controlling the outcome more deliberately. Something to think about, how understanding limits gives you more control.
Good point. Lots to consider beyond just the numbers.
It really is. Well, that brings us to the end of this deep dive. Thanks for joining us as we unpack the world of chemical quantities.